Have you ever imagined what happens if a generator suddenly loses its excitation or if the prime mover stops working? In this video, we will discuss about loss of excitation and loss of prime mover, their causes, effects, and how protection systems safeguards generators from these conditions. The generator delivers both real as well as reactive power to the grid. The real power comes from the turbine while reactive power is due to the field excitation. Consider a generator delivering the complex power to the grid. Corresponding to real power PE, there is a shaft mechanical power input PM, and corresponding to reactive power QE, there is a field current IF. Now, consider that the field excitation is lost while mechanical input remains intact. Since the generator is already synchronized with the grid, it would attempt to remain synchronized by running as an induction generator. As an induction generator, the machine speeds up slightly above the synchronous speed and draws its excitation from the grid. Now, there are two possibilities. Either the grid is able to meet this reactive power demand fully or meet it partially. If the grid is able to fully satisfy this demand for reactive power, the machine continues to deliver active power of PE megawatt but draws reactive power of QLOE from grid, and there is no risk of instability. However, generators are not designed as an induction machine. So, abnormal heating of rotor and overloading of the stator winding will take place. If the grid were able to meet the reactive power demand only partially, then there would be reflected by a fall of the generator terminal voltage. The generator would be underexcited. There are certain limits on the degree to which a generator can be operated within the underexcited mode. Therefore, the operation in case of loss of excitation must be quickly detected, and the simplest method by which the loss of excitation can be detected is to monitor the field current of the generator. If the field current falls below the threshold value, a loss of field signal is raised. In case of loss of prime mover, that is the loss of mechanical input, the machine continues to remain synchronized with the grid, and which is running as a synchronous motor. The machine now draws a small amount of active power from the grid in order to drive the turbine and meet the losses taking place in the machine. At the same time, the machine supplies reactive power to the grid since its excitation is intact. Running in this mode is not harmful to the generator, but it is definitely harmful to the prime mover like steam turbine. Normally, loss of steam supply to the turbine causes loss of prime mover. When the machine runs as a motor, there is objectionable temperature rise and which cause damage to the blades of the turbine. Therefore, loss of prime mover needs quick detection followed by tripping of generator. When the prime mover is lost, the generator starts drawing real power from the grid and supplying reactive power to the grid as before. The real power drawn from the grid is quite small compared with the generator rating, which is just enough to meet the losses. Therefore, the magnitude of stator current is smaller than when it was generating, but the stator current undergoes 180-degree phase shift. This suggests that if we use a directional relay with an angle of 180 degree, then it would detect the loss of prime mover. However, the magnitude of this reverse current is quite small compared to the forward current. Therefore, the directional relay for detecting the loss of prime mover needs to have a high degree of sensitivity compared to directional relay used for overcurrent applications. So friends, now you know what really happens during loss of excitation and loss of prime mover. If you found this video useful, don't forget to like, share with your friends and drop your thoughts in the comment box. And of course, subscribe to the channel and don't forget to press the bell icon. Till time, keep learning, keep growing. Thank you.